Hello, it's Keith here, and we're going to be doing a special episode today on the Spectrum Next. Now, this is something that's been requested by a couple of my patrons before now. The Spectrum Next is a sort of new upcoming Spectrum alternative. It's a recreation with some added hardware. I believe they did a Kickstarter a couple of years ago. The basic boards are now available to people. I think they're still waiting on the complete ones with a full new keyboard. Unfortunately, you can't buy the hardware yet if you didn't back the Kickstarter. But we do have the emulator zesarux, I think that's pronounced, maybe, which will allow us to simulate the Spectrum Next, and so we can play with the hardware and learn how it works. Now, fortunately, the machine is actually underneath is a basic Spectrum. So if we create a working Spectrum Hello World example, it'll work just the same. And so then when it comes to using the extended hardware, which you can see here, this is the 256 color mode with my font showing. Well, we can just then build on that with the extra commands we need. So today I'm going to talk about how to set up zesarux with the extra software to get the emulation working for the Spectrum Next, because there's a few tweaks you have to make, and how I've got it working with my build scripts, and so we can see how we can make a valid example, and then I'll look at the code and how this works. Okay, so the emulator is free. You can just go ahead and download it. But then when it starts up, we do actually need to select the correct machine type. The machine type is known as the TB Blue. I think that's the code name of the Spectrum Next. So we'd need to select that. We then need to enable the MMC, because by default the system needs a boot disk. Now we need to specify the MMC that comes with the emulator, turn on MMC emulation, and turn on div MMC ports, otherwise it won't start correctly. Now, I did have a problem with that, because while that would start the emulator up, all I got was a green screen and a load of beeping, and even once I'd got past that by fluke, I think really, I couldn't actually get the enhanced options working correctly. It seems you need to go into the settings menu, display, and then turn on real video, this option here. So we'll have a look at the emulator and we'll see all of that in action. But once you've done all of this, that should get you working with the Spectrum Next on this zesarux emulator. Let's have a look at it actually working. So if I just start at my example code here, I've got a new script called ZXN here. So we'll just start this. I'm compiling with my regular VAS assembler. The Spectrum Next does have some new non-standard Z80 commands, but I'm simulating those and we'll have a look how. And my build scripts for making the TAP file are exactly the same. So if you don't know how to make a TAP file, please see my ZX Spectrum Hello World example, in which I went over a great deal of detail about how to do that. Now, when it comes to this emulator, if I just press F5 here, and we've got this storage menu here, and then MMC. Now, this is where you need to set MMC emulation. You need to specify the file, which, as I say, comes with the emulator, and you need to enable this div MMC ports. So that's the first thing you need to do there. You need to go into machine here, and you need to select this, I can't pronounce that, and then TB Blue here, which is the machine. Now, as I say, I had some trouble with the display, so I had to go to display and enable real video. If I turn off real video, you see I get no enhanced graphics. So as far as I know, I don't know, the auto detect maybe isn't working for some reason, I don't know. Anyway, so I've had to enable that to get this example working today. And as I say, before that I was just getting this blank green screen with this crazy beeping sound, but when I turned that on, I could then see it was doing a monitor calibration, please select your resolution kind of thing. So it seems quite odd that that's disabled by default. Of course, this emulation's still work in progress, so who knows, maybe it'll be different by next time. Okay, so that was what I did there. Now, one other setting I'm using here, this is quite a good one if you're developing. If you go to hardware here, you've got this TB fast boot mode, and I've got that switched on. Now, by default, the firmware will start up and it will do a sort of boot sequence. It's very slow though, and I'm just loading from a tape image. So if you select this, it basically sets the firmware to a 48K Spectrum, but then you can load a tape file into that and turn on all the extra hardware as if you've booted to the real machine. So you're just basically skipping the disk support and things like that. But as I say, for doing this example, this was exactly what I needed. So if I just disable that here, and then if I go to back and I go to hardware, machine here, and this one here, and then select TB Blue, we're now booting, you see, and we've now got the boot sequence that you would see if you actually started this normally. And you can see it's loading here, and now it's booting up to the Spectrum menu. And we're waiting again. Still waiting. And there we go. So as I say, that's why I'm not using that. Now I'll just show you what I'm actually using. So I'm compiling with Vasm, my usual assembler. The script I'm using to build that is identical to normal. So as I say, please see my Hello World on the ZX Spectrum if you don't know how to build a file with an assembler. So if you're really new to this sort of game, then you would want to see that as well. Because as I say, anything that works on the regular Spectrum will work on this. It's just you've got these extra options for the hardware sprites and things. So if I just find the right line in this massive file now, where is it? Here it is. So I've created a few extra lines in here in my file to start the emulator with zesarux, if that's how it's pronounced, rather than fuse, which is much easier to pronounce. So I've got lots of switches here. I'm specifying a tape file, and this is going to be the tape file that I've created with the rest of the script. The machine type is TB-Blue, which is, as I've said, the Spectrum Next. We're specifying an alternate config file because by default it saves in your user profile. I prefer it saving in the current folder. I've got this fast boot mode here, which is what we saw before, where we're skipping loading the MMC firmware. Disabling the splash screen, get things started up fast. Disabling the welcoming message, getting things started up fast. Quick exit, getting things to close down fast. So this is a much easier way of doing things. And I've put this on my website, so you can just go ahead and copy and paste it into your own scripts if you've got them. Okay, so that's how we can get the emulator to start up. I'm hoping you've got some kind of assembler that you can compile a Spectrum file with already. So if you haven't, as I say, please have a look at my website with that Hello World example where we went over that. All of the source code for today's example is available for download. I've also got my regular Spectrum tools which are available for download, but I'm not putting the scripts for today's example in. The source code's available, but not the build scripts. And the reason for that is this is all unfinished hardware. The firmware could change at any point. The emulators could change and probably will. So I'd say you're welcome to the source code. You're welcome to create your own build scripts, but I don't want to rebuild all of my tools and then the emulators change or the actual firmware for the Spectrum Next changes and nothing works anymore. So I'm just a bit apprehensive on that at this stage because, as I say, I literally only learned how to do this yesterday. So so this is a bit of an introduction. I'm still learning this myself, but I really wanted to do this because I want to see how much interest there is in the Spectrum Next and to see if it's worth me pursuing this further, because for me, I've got lots and lots of classic systems I can be covering, both Z80, 6502 and many other formats. So I want to check if people are interested in this. So if you are, please leave a comment, whatever, so that I can see how much interest there really is in this format and this platform. Okay. Now, onto the Spectrum Next and the source code. So let's just have another quick look at that example and see what it did. So thanks to my command line settings, we've got no boot sequence there again, very quick. So we're printing Hello World, we're printing a background pattern here of all 256 colours, and we're running the monitor and the mem dump, which we use in my regular tutorials because these are what I use to fix problems when I'm learning about a new system. So that's what we got. Now, the Spectrum Next is a Z80 processor, but they've programmed in some new commands that don't exist on a normal Z80. And one of these is known as Next Register. Now, this is Spectrum Next, of course, not Move Next. The Spectrum Next has up to 256 sort of special hardware registers that do things relating to setting preferences and things. So they've created these special commands to use these. Now, of course, Vasm doesn't support these, but these are byte code. So if we put the bytes into our code, then it'll work just fine. And so what I'm doing is I'm doing ED91 here, which is the equivalent of this next reg command. And then there is a numbered register, and then there's a numbered value. And the register isn't A, B, C, D, etc. It's a number 0 to 255 within the hardware, and we'll be looking at a few of those and what they do. And then there's another one here that just uses the accumulator. Now, if we have a look on my website, I'm trying to document all of these new commands, what the macro you can use if your assembler doesn't support them, how we can do it. And if you really don't want to do that, you can, in most cases, I think, you can simulate them with equivalent commands. You see, writing to a next register is the equivalent of selecting that register with port 243B and then writing the new value to 253B. So this command here should be the equivalent of this byte code here, or this next reg command if you see that in your assembly code. So as I say, you've got options there if you don't want to use it, but we're going to be doing a lot of these next regis, so I've set up these macros to simulate the commands in my assembler. Now, when we start our program, we do it in the exact same way as a regular Spectrum. Now, my tape file is set up to load at address 8000, so that's what I've done here. And then we're going to start up just by disabling interrupts, so I don't want any trouble. So we're going to just start here. And what we're going to do is we're going to set up our palette, because we're setting up a palette, and I don't know if you've noticed, I'm simulating an Amstrad CPC palette because that's my system that I learned on. So we're selecting the first palette here for layer 2, and then we're selecting palette entry 0. There's 256 entries in the palette. So we're using these registers here. So register 43 selects the palette, and register 40 selects which index of the palette we want to change. So all we're doing is we're writing a 0 to register 40 here within the next, and that's selecting our 256 color palette base. Now you can see we've got this address my palette all the way down here. So here's the colors I'm defining. So the palette's quite interesting. It uses a single byte per color. So you've got 3 bits of red, 3 bits of green, and 2 bits of blue. So, okay, bit odd, but that's the way we're doing things, so that's fine. And so I've defined the background as dark blue here. I've defined the first color as yellow, the next color is cyan, and the final color is red, just to 4 colors. Now, the rest of the colors are defaulting to all kinds of crazy random colors, so that's quite handy for our testing. So we've got this palette loop here. We just read in a byte from my palette, increase the source address, and then we write A, the accumulator, which we read in here, to the register 41, and this is setting one of the colors, and I guess it auto increments because we can just keep writing away for all 255 colors if we want. So we're just looping around here, filling in our palette, in this case of just 4 entries. So now we've got a palette set up. That's quite nice. But the next thing we want to do is we're just going to set up the screen with some standard defaults. So what we're doing is we're setting the scroll to 0 here. This means that the top left byte of the data in memory is the top left visible byte. So this is for a hardware scrolling effect. You can hardware scroll the screen, which is quite nice. You can also change the size of the screen. We're setting the top left to 0,0, and we're setting the bottom right to 255 by 191, which is the normal 256 pixels, 192 tall screen. Now, if we change these, we can make the screen a different size, and we'll have a look at that in just a moment. We can also define a transparent color. Now, one of the color entries can be defined as being transparent and will show through, in this example, to the Spectrum background. So you saw it before, it had that blue Amstrad CPC style background, but if I enable this here with Reg 14 and write the bottom bit as bit 1, which was the dark blue of the background, because this is in red, green, blue format it seems. I was expecting it to be a palette entry, but it's not. So we can run that, and that will make the background transparent. What we can also do here, if we just change this to 128 and assemble again. Well, we've now got half our screen missing. You see all the right-hand side's gone here because we've set that to just half the width of the screen. And you can also see the blue is gone, and we can now just about see the loading commands in the background of the original Spectrum screen. So, I mean, maybe you could, I guess you could do some clever parallax here, and I know there's some other hardware modes with more enhanced Spectrum color modes, so maybe if the Spectrum modes have been enhanced enough, maybe you could do some nice parallax with that. But anyway, it's certainly there as an option. It's quite an interesting idea. And as I say, you've got these hardware scrolls as well. We can just try those out. If we just change this to 128 and this one to 128 and compile again. So now the top left of the screen is right in the middle almost. So you say we've got a hardware scrolling option, and we can now see that background much more clearly. So yeah, we've got some clever options here. Not very useful for today's example, but it shows the potential for the hardware. So that's how we set up our screen. Now we want to turn it on. Now, there are multiple options for accessing the screen memory, but I'm going to use the simplest. The advanced one is where you page the entire RAM into certain areas of the Spectrum's accessible memory, but the easier one for us as a beginner is to actually use the ROM area. Now, if you think about it, ROM means read-only memory. So if we write to the 0 to 3FFF range, nothing would usually happen. Well, the hardware allows us to actually use that range to write to part of the screen. Say part of the screen, because that range is just 16 kilobytes, and the 256 color screen is, I believe, 48 kilobytes. So we can only write to a third of it at a time. Now, we've got some bits here, and we write to port this time, a normal port, not a next reg. We write to 123B. Now, if we set the bottom bit, we make the screen writable. If we set the next bit, we make it visible, which we certainly want to do. And then the top 2 bits here will select one of the banks of the screen, because as I say, we can't access all of the screen in one go. So we're accessing the first bank here, and then we're writing to the screen. So you can see here, we've written this area here. Now, how are we filling that in? Well, you can see the code just here. It's very simple. We set the accumulator to 0. We set the number of bytes to 16 kilobytes, the start address to 0. We just write the accumulator, we keep incrementing it, and we just keep looping around here until we've written 16 kilobytes, because we can't write more than 16 kilobytes because we would go into our real RAM areas and we'd probably corrupt the stack or the regular screen or something. So as I say, we can only access one 16 kilobyte chunk here, but we could access the second 16 kilobyte chunk in the same memory range just by changing these bits here. So if I put a 1 here, changing the bank we're selecting here, and I run again, well, now our gradient effect is down here. And if I just change it to 10, well, now it's right at the bottom. So you can see we've got 3 banks here, but the text's still at the top. Well, why is the text at the top? Well, my text writing code is working all of this out and switching to the correct bank before it draws the text. So this is just for my example test pattern here. So that's what we've done there, and we've now got this print string command, and we've got a monitor and a memdump. We're not going to cover monitor and memdump. Those were in my multi-platform tools. They're the exact same code, unchanged. And the print string routine is the exact same one from the Hello World example. It just prints a character 255 terminated string, which is what I do in all of my tutorials. We're using the exact same font as we used in the bitmap examples in the past as well. And this time we're going to convert that, and we're going to show bitmap characters to the 256 color screen. But first of all, we need to have a way of selecting a pixel on the screen and working out the byte address and paging in the bank. So that's what we've got here. We've got a get screen pos command, which is going to do all of that work for us. So our screen is 256 pixels wide, and each pixel is 256 colors, which means 1 byte per pixel. So if we have a 256 pixel wide screen, 256 bytes wide, then effectively our X position is just the low byte of a 16-bit pair, and our Y position in theory would be the top byte of that 16-bit pair. But we are splitting into 16K banks with the addressing mode that I'm using here, the simple addressing mode. So what we do is we take all but the top 2 bits of our Y position and use that as H, and then we take all of the bits of the X position and use that as L. And then we take those missing 2 bits that we ignored here, that we didn't put into H, and we use those as the banking selection for that port 123B here, and we just out to that. And so what this does is it makes the bank visible, it selects it for writing, and then it selects that for the place we want to write to. So this get screen pods command, we can just give it any pixel on the screen in B and C, and it will select the bank, give the HL address for the equivalent area within that ROM section 0 to 3FFF, and then we can just write away to HL and we'll be fine. And because each line is 256 pixel wide, if we want to go down a line, we just increment H. Now the only problem with that would be if we went over the third, but because we're working in 8x8 character blocks in this example, we don't need to worry about that. Now the print character routine is going to use an XY virtual cursor, so we've just got some memory defined for those. We've got a simple new line command here, so we just set the X position to 0, and then we point to the Y position just by doing an inc, because the Y position is just after the X, and we increment the Y. It's got no clear screen and it doesn't cope with scrolling, just very simple, but enough to get us started and allow us to run that monitor so we can debug when things don't work how we expect. So we've got a print char routine, pushing all of the registers modified in this print char so that we know that when it exits, everything's the same as when it started. And this is how we're going to do our font. Now, our font file that we use in these tutorials, this font 96 or font 64, if we're on a limited system, is it's a 1 bit per pixel font, so it's a basically native Spectrum format font. Now, we're going to have to convert it to 8 bits per pixel today because we've got a 256 color screen. So that's what we're going to be doing. Now, the first thing is this font doesn't have any characters below 32 because we don't have really much spare memory, to be honest. So we subtract 32 so that we can calculate the correct location in this font. And then we need to multiply by 8 because there's 8 lines per character in the font. Each line is 1 byte, so 8 bytes per character. So we're effectively multiplying the character number by 8 to get the offset within the bitmap font. We just then add that in, and now we've got the correct memory position for the font that we're going to read from. So we store that in DE here. That's in DE now. Next, we're going to get the position we're going to write to on our screen. So we get our X position and our Y position. Now, each character is 8 by 8 pixels, and each byte is a single pixel. So we need to multiply by 8 the X position, and we need to multiply the Y position by 8 because there's 8 lines per character, and then we run our get screen pos. This will return the memory destination in HL, and it'll also deal with our banking. So now we just need to actually get the pixels from our font to our screen. So we've got 8 pixels per line. We're using B to calculate that. And we've got 8 lines per character in total that we're going to show. So what we do is we load in from our font here into the accumulator. We just back that up into C. And then we shift 1 bit off the left-hand side into A, the accumulator, and when we write that to the screen. And we do this 8 times, taking 1 bit each time and putting those into a byte to be shown to the screen. And this has the effect of setting the font to color 1 within our palette, which is why it looked yellow on the screen. If we put an extra rotate in, we could make it a different color, but that's what we're doing here. We're setting it to color 1. So we repeat for the 8 pixels here. We then restore the original address because we now need to move down from the starting line to do the next line of the font. So we restore HL, so we get back before we'd moved across here. Increase H, which as I say moves us down a line, and move to the next line of the font, and we're using IXL as a counter for the lines here, so we just repeat until we've done all the lines. Once we're done, we just need to increment the X position of the cursor for the next character that's printed. Check if we're at the end of the screen. If we are, we need to run that new line function. And that's really all there is to it. Now, it's quite long, but it's just because, say, the font's not really in the right format for the screen, so a bit of bit shifting going on. Anyway, though, this has got enough. This has been enough to get the example working today. And as I say, now I've got my memory dumper and my monitor. So if I'm playing around with sprites and things aren't working quite right, I can maybe debug things. So anyway, you can see there, that's the example, and I'll just fix it back up again if I just get things back to the way they were. So there we go. So this is how we can do the 256 colors, use the extended hardware of the Spectrum Next, and of course get our emulator working at all. So if you liked what you saw today, please let me know, because I'm still in two minds about whether to do more of these tutorials. Anyway, I'm hoping to do the Commander X16, I think it's called, which is a 6502 system that's coming out soon, again in an emulator. So I'm going to be playing with these new experimental systems just to see what the response to them is, because I say personally I'm a big fan of the older systems like the PC Engine or the Neo Geo or the Turbo R, you know, for my really powerful hardware, but I know there's a lot of interest in these newer systems as well. Let me know what you think. Anyway, thanks for watching today, and goodbye. If you enjoyed today's lesson, please check out my website. We've got tutorials, source code and development tools for 6502, 68000 and Z80 systems, and a lot more systems coming in the future. We're going to be covering the 8086 and the ARM and a few other things as well going forwards. And if you've liked this lesson, if you've got questions, comments or suggestions on how it could be made better, please consider signing up to my forum. It's free, of course, and you can come along here and you can make suggestions, you can ask questions. And if you've got assembly projects you're working on, please let us know what they are. Maybe show off a few screenshots, tell us what things you've found interesting or what tricks you've come up with, because we'd love to know about it. Anyway, thanks for watching today, and goodbye.